We're going to wrap up our discussion of solids and move into some aspects involving materials. Materials will cover both today and then also Monday, but we're going to have to be selective. There's a lot of great ideas within Atkins discussing materials, any one of which could be a semester-long course. So we're going to have to be selective, and I'm going to be choosing a subset of that information to share in class. But first of all, let's wrap up our discussion of solids. So we saw previously that we had different ways to describe the structure of solids, and we were looking more closely at that crystalline structure uh, by looking at metallic solids and how we could describe the arrangement in a unit cell that was then part of a repeating pattern. The arrangement for the metals, if you recall, in that case, all of the spheres that we were stacking together were all the same size. So we were looking at what does it mean to stack up things that are the same size, whether they're atoms or inches. And we saw that we could place them into different layers, different arrangements. In this case, for our metals, the coordination number was 12. This is the maximum density that we can have when we're stacking spheres together. They're the same size. This would be the maximum coordination number, the greatest density. When we then look to see, well, how specifically are they constructed, we brought up three different unit cells that we were interested in, all different aspects of ones that were cubic. And one thing that we did was we accounted for how many atoms were contributing to the unit cell. Now, I don't mean an atom when I say it's 1/8 of an atom when it's on the corner. I don't think I've cut the atom in half. What I think I've done is I've considered this representation like I see it the right, where I have a particular arrangement of atoms, and then I'm mentally superimposing a cube on top of that, and I'm asking the question, is a particular atom within that cube, partially in the cube? I'm not dividing up the atoms. This is just my bookkeeping to say how many would be contributing to a unit cell. One thing that we can think about with that then is, well, what would be the density of the unit cell? So density involves mass and volume. The unit cell is important because we need to calculate how many atoms are contributing to that particular unit cell. We want to account for their mass and their atom and the number of atoms to get the total mass of the unit cell. And we also need to know the arrangement when we're now going to account for the volume. We want to be able to think about the spheres and how they're arranged. Are they touching along an edge? Are they touching along the diagonal of a face? We want to be able to consider how they're touching and use that back to be able to calculate the volume. So let's see how this applies if I'm looking at an element like nickel. So elemental nickel, it says, adopts an FCC structure. That's face-centered cubic. And the spheres of the nickel are a radius of 125 picometers. So first thought is, this is my face-centered cubic arrangement. How many atoms of nickel are in that? I think there are 4 nickel atoms per unit cell. So pause for a second. Do you see that as well? What I'm trying to visualize within that, 4 atoms because I have all 8 corners, all with a 1/8 contribution, and then I have the 6 faces all at 1/2, so I get 4 nickel atoms contributing to the unit cell. I can use that to determine the overall mass. So the way I would do that is, if I look at the periodic table, the molar mass of nickel is 58 and change. That's when I have a mole's worth of atoms. What if I don't have a mole's worth of atoms? I only have 4. Really small number in grams, even smaller in kilograms, and it should be small. This would be the mass of 4 nickel atoms. If I want density, I also then have to get the volume. So I'm going to recognize this is a face-centered cubic, so I have to consider where are the radii touching. For a face-centered cubic, it's along the face here, along what's called the face diagonal. So if I use the Pythagorean theorem here, I want to connect that to the length of a side. So within our cube, let's call the side length a. A squared plus a squared is 2a squared. 2a squared then is the face diagonal. Thinking of it back in terms of the length of a side. So 2a squared, the face diagonal, would be this value. This is 4 of the radii put together. Because if I look in the image, 1, 2, 3, 4, that's a value in that's my particular value there in pico that I've converted to meters, picometers to the that I've converted to picometers. Then within here, I've now connected it back to say what would be the length of a side. And then if I want the cubic volume, that's what's going to be the side cubed. Putting that all together gets me the density. So if I step back and say, what did I do here mathematically? How did I conceptualize this? I had to first recognize what information do I have if it's face-centered. Let's use that information to determine the total mass of the unit cell. And then let's also use the information of face-centered cubic combined with the radii to come up with the volume. That's where I come up with the density. And I find it remarkable, this density of the unit cell, that's the same as the density for a large macroscopic piece of nickel. So we've been looking at unit cells and how they apply for metals. Let's consider now how they would apply for ionic solids. So we're going to be arranging these once again within a unit cell, but we have to account for the fact that they're not all the same size, they're not all the same charge. We're accounting for both the stoichiometry and it has to be electrically neutral throughout. If you look within the stoichiometry and what it's trying to show us within the size, the anions here are being shown larger than the cations. If we think back to our periodic properties, that's a pattern that we saw. So the way that we can begin to now think about how it's constructed, let's take the larger spheres. Those would be the anions. Let's have them adopt a structure similar to what we saw with our metals. The cations, which are smaller, let's have them accommodated by placing them in the spaces in between, in what it's calling the different holes that you would have present. Now, what does it mean, holes? This is what we had before. We took a layer where they're all the same size spheres. We put another layer on top of it. But notice we still have these spots in between. The spots in between are holes that have different coordination numbers. Some are octahedral, some are tetrahedral. Because the cations are smaller, let's place those within the holes. So we'll be first adopting a structure based on the anion, similar to what we saw with our metals. And then we will be adding the cations in the smaller holes. Now we have different ways that we can do this. So here I show a few different examples. We need to, within our analysis here, have to match the correct stoichiometry. And we also need to consider how the size of the ions will be affecting the structure. So if we look within this, we have the several different crystal lattices. We saw what it means to have a primitive cubic lattice, face-centered cubic. The different structures that we see at the bottom, some of these have what you might say is common names. So this sodium chloride structure, there's other crystalline solids that adopt that same structure. It's called the rock salt structure. Don't worry that much about the common names, but that's what it's saying, that it's not every single ionic compound is a unique structure. There's different common ones that are frequently encountered. But now, notice within this, when we're placing our atoms and constructing it, we need to be able to have something that matches the stoichiometry. So when we were looking at our metals, we took our different lattice points and we put atoms at all of those. We're going to do something a little bit different here when we're looking at the ionic compound. Instead of placing an atom there, we are going to place a combination of atoms. For these, we'll be placing a pair of atoms at each of the different lattice points. What we're placing, that's called the motif. So for each of these different lattice points, we're going to place these combination of atoms. Chloride, cesium. And it's also designating that we're going to place them and they're going to be slightly offset this way, or side by side, or offset this way. So if we look at this one, these two atoms, if I place the green one at all of the different lattice points, I would have one example where, because the cesium is offset there, it would be placed then in the center of the unit cell. Where are the other red atoms? They would be placed offset, but they would be out of the unit cell. That doesn't bother me with my math because I am still going to be able to do my bookkeeping and see that I have 1 cesium atom, I have 8 chloride atoms at the corners, 1/8 contribution, so my stoichiometry would come back to be 1 to 1. If I look within the rock salt structure here for sodium chloride, I have my different lattice points, and at those lattice points I'm going to add the motif. So if we just take this top corner, I'd have chloride, sodium next to it because that's my motif. I've taken sodium, put it at one lattice point. Right next to it would be the chloride. Right next to it would be the sodium. I've got a lattice point right here in the face. That would be that atom, and next to it would be the sodium. See if you can visualize that. So what we're doing here is we're using the different lattice points, but instead of placing a single atom there like we had with a metal, we're placing a combination of them. We're placing our motif, and that's being used to then populate the unit cell. Now, let's look a little bit more closely at these features then. So these are the same three. We can look at different parameters within the table. I see information about the size of the cations and the anions, a ratio involving those, and then the coordination number. So for the coordination number, that's our short range order, the immediate neighbors. It looks like I see examples where the coordination number might be 8 for both, 6 for both, 4 for both. So one thing that it appears here is that when the stoichiometry is 1 to 1, cation to anion, same number of cations, same number of anions in the empirical formula, the coordination numbers appear to be the same. Now we know there's ionic compounds where the ratio is not 1 to 1, so let's look at those. So these are different cations paired with the oxide anion. Lithium, magnesium, scandium. So lithium oxide, magnesium oxide, scandium oxide. Notice what we have here. The coordination numbers now, they are the same when it was the 1 to 1, but they begin to differ when the empirical formula is not 1 to 1. What's going on there? How do we make sense of that? It turns out there's a really clear pattern to this. What we see is that a ratio involving the charge of the cation and its coordination number is the same in proportion to the charge of the anion and its coordination number. So if I look, first of all, with the magnesium oxide, plus 2 cation, coordination number is 6. Minus 2 anion, coordination number of 6. Same proportion. Take a second, see if that reasoning then works if you're looking at the lithium and the scandium. Just to work through for the lithium there. So the lithium was plus 1, coordination number of 4. Oxygen minus 2, coordination number of 8. Yep, in the same proportion. It will work every time for our ionic compounds. Why is this coming about? Well, let's think back to when we were first looking at the structure of an ionic compound, and we envisioned it all being in a straight line. So we could have an anion with 2 cation neighbors, then the cation with 2 anion neighbors, then the anion with 2 cation neighbors. So I would be saying that all of these have a coordination number of 2. They all have this, in this case, I would say the same charge and a coordination number of 2. The charge is being distributed across both of those neighbors. Don't really want to say distributed. I know I did. It's not like it's now being strictly divided up, but it's acting on both of the immediate neighbors. And my point being is that you'll have an imbalance if this same thing was set up and let's say it was minus 2 plus 1. As you would go on, the charge wouldn't balance. You need to have this electric neutrality throughout. So you need to be able to accommodate that by having differences in the coordination number. That's what's taking place and why we see this pattern here. Now, I also see in the table a ratio involving the size of the cation and the size of the anion. And it appears as that ratio changes, even though the coordination numbers are the same for the cation and the anion, they're changing as well. So the way I make sense of that, let's first of all consider we're putting the cations in the holes that we have within the structure. If we have a case where they're similar in size, the cation is capable of making sure that the anions are not right next to each other touching. It's able to spread them out. What would be the case if the cation gets smaller? It's not as effective then at being able to stretch and move and separate the anions. This would be, as it's describing, the limit of that. If it becomes even smaller, notice it's even less effective at trying to keep these negative charges away from each other. So what we're seeing here is the size of the cation relative to the anion, it has implications for the structure. Turns out there's a particular ratio that one would find as far as if you're thinking about the size of the ions, and what does that mean then for the coordination number. The ones that we're most frequently encountering is where the cation is either tetrahedral, octahedral, or in a cubic arrangement. That's what these coordination numbers of 4, 6, and 8 correspond to. I don't want you to memorize a particular radius value as a threshold value, but I want you to understand the concept for why if we're changing the size of the cation relative to the anion, it leads to a change in the coordination number. Now let's practice visualizing and working through some of these unit cells. So here's two different representations of the same unit cell. Sometimes having two different representations help because you get a little different perspective to see what's going on. So first task for you here, try to determine how many nickel atoms are in the unit cell, how many arsenic atoms, and what would be the empirical formula. I'm choosing this one in part because my hunch is you don't know the stoichiometry for nickel arsenide. See if you can figure it out by inspecting the images. Now, if I look at this one, I'd say in this case, I think the arsenic's easy to see. If I look, perhaps not with the image on the left, but certainly from the one on the right, if I look top down, those two atoms are directly within the unit cell. So those would be contributing 2 atoms of arsenic. How about the nickel? Well, I see 8 different corners. We've done the math on those before. We also have a new position here along the edges. So how do we account for that? I think the nickel 8 around the corners, all at 1/8. For the edges, a given one would be in 4 different neighboring unit cells, 4 times 1/4. So I'd say in this case, the stoichiometry ends up being 1 to 1. I see a total of 2 nickel atoms and 2 arsenic atoms. Let's see if we can do the same thing. Here's a question from the end of the chapter. So this is looking at a structure called rutile, TiO2. It shows a unit cell, and I've added this additional image because I think it helps give a different perspective on it. So if I were to do my math within this case, accounting for them, I think the titanium is easy. The titanium, I see 1 in the center, and then I see 8 on the corners. 1 plus 8 times 1/8, 2 in the unit cell. For the oxygen, it's perhaps not quite as clear. I see ones within this image on the right where it looks like that oxygen atom is right on the face. But it's perhaps less clear if these other ones are they within the unit cell? Are they along the face as well? When we do our analysis here, it all has to stick together. It all has to stick together, and by that I mean we also have insights in terms of the structure if we consider the coordination number and the charge. It needs to work out for TiO2 as well. So if I look at this, I think my oxygen atoms are -2 and the titanium is +4. If I were to think about the coordination number, if I look at the titanium, I'm confident that has a coordination number of 6. If I look at that central atom, I see absolutely 6 oxygen neighbors around it. So if it has a charge of 4 and a coordination number of 6, what has to work out for the oxygen? Oxygen in my empirical formula is -2. So that tells me it has to have a coordination number of 3. Back to this idea of how it's the same proportion. Coordination number of 3, that's a trigonal planar. If I look within my picture here, this oxygen atom, absolutely. Coordination number 3, trigonal planar, it all fits together. Now, when I mentioned that the topic of materials, there's a lot of ideas within Atkins. I like this idea within Perusal that started with wow. We're going to have to be selective within this. We'll start looking at some ideas today, and we'll pick up more ideas next time. Uh, Within the first section in I, my main thing I want to look at within that is the topic of alloys. And we're going to start a discussion a little bit about uh, electron conduction as well. So for an alloy, you take two or more metals, melt them, pour them together, and you can have different compositions within that, and they have different properties after they then crystallize. You can have examples that are homogeneous, where you have the atoms that are distributed uniformly throughout, or heterogeneous ones, where you have different crystalline phases present. There's this image that's shown of what you see in an example of a heterogeneous alloy taken with an electron microscope, which is an amazing instrument where you see different regions. Now, when I say that you take it and melt it, notice within this one, several of these are alloys that I think you've probably heard of before. I think you've heard of brass or bronze, stainless steel. Let's think a little bit about how you would make this. So bronze, that's typically a combination of tin plus copper. So you'd have to get a source of tin. The mineral cassiterite is an example. So you could take that, you could mine it, you could smelt it, meaning you could heat it up and remove the impurities that weren't tin from that. You could then add that to molten copper. That would make this alloy called bronze. So this particular technology, I find it fascinating. Well, when did this take place? Well, the Bronze Age, it's not like they had a modern factory in order to do this. The Bronze Age, notice, this began 3800 BC, before the invention of the wheel. I find it fascinating that here's a technology that early man was able to put together even before we had farming across Europe. Just amazing that this is something that was developed and come across, invented in that era. So what's taking place? So if we're going to have two different things together, two different types of atoms, we've got different ways we could do it. Well, one would be where they're very similar in size. If they're very similar in size, they can substitute directly. Meaning, okay, let's take out one of the atoms in this picture that's orange and put in another that's blue. You can do that when they're comparable in size. We find that the structure then is affected. It's no longer the property of just the original atoms. And the properties, therefore, are affected. So there's differences, for example, in the electrical and thermal conductivity. It's different than the original pure element. You also find within this, it doesn't become as mobile. The atoms themselves are less mobile. It's more difficult for the atoms to slide as you've distorted aspects of the crystal lattice. So it turns out a feature of that it becomes harder and stronger than the original metal. If you consider something like steel, steel is different. Within steel, you're taking iron and you're adding in carbon atoms. Now, carbon atoms are much smaller than the iron, so they don't substitute and replace. Instead, they're populating now holes within the structure. This is called an interstitial alloy. Once again, the properties are affected. So in order to do this, the atoms that you're adding, they need to be small enough to fit into the holes. That's why there's a size constraint. Several of the properties you find affected are similar to what we had with the substitutional alloy. If you're restricting aspects of the motion, for example, you're once again making a harder and stronger material. Briefly looking at silicates. So this is the most important class of minerals on the planet. Many, many minerals are silicates. There's a lot of diverse structures to this. If you recall, the SiO2, that was described as a covalent network. Carbon in a diamond form, we have this extended covalent network, both tetrahedral in each case. But within diamond, we have a single crystal structure, whereas when we're looking at these silicates, we have many, many different ones. The reason why is that even though we're looking at these SiO4 tetrahedra, you've got a lot more variability around the angle with the oxygen. It's not always 109.5 throughout like a perfect ideal tetrahedral. This leads to many, many different ways that you can put together these tetrahedra. Different sheets, different ring structures, really a lot of diversity here, and many minerals reflect this. Looking really briefly at calcium carbonate, I find this one really interesting because here it is something that we use as a technology as far as a building material, part of concrete, and yet it's also found in nature, in our bones. I find it really fascinating that's in both domains there. One thing to draw your attention to, if we look at the crystal structure here, uh, we have these blue cations that are the calcium, and notice how they're next to the carbonate anions. These carbonate anions, I'm seeing them as being the trigonal planar. So if I were to think about that in my VSEPR description, I agree with that. And notice how they're all aligned. I see this alternating pattern, but they're all in the same plane, pointed in the same direction. In order to go, if we had, let's say, this melted and we wanted to crystallize it, all of these would have to adopt that same alignment. This is what it means to say something is a liquid, and then when it forms a crystal, it all adopts the correct alignment. If you think back to our ionic liquids, we said one way that you could inhibit this was that when the anions that you had, uh, excuse me, the cations in that case, were these bulky asymmetric ones. It was saying that they would not readily adopt the correct orientation. I using this as an example because this really, to me, illustrates what does it mean to say that the um, ions had to adopt the correct orientation when they crystallize. Looking then just really briefly to get started on this one, in J, this will give us some insights of where we're going to be going. So in terms of the bonding that we have in metals, an initial model would be a sea of electron picture. So we know that metals, low ionization energy, let's envision them as having lost their electrons. We have now a whole array of cations, but instead of taking the electron and putting it on a specific anion, let's have them delocalized and distributed throughout. This is what it means to say there's a sea of electrons. You're taking the electrons and you're delocalizing them. This does a good job of explaining some properties for the metal. It could be malleable, so you could distort the structure because you could twist or turn this and you still have the electron glue that would be holding it together. It also would explain aspects of conductivity of being able to have the electrons travel throughout. Now, if we look more closely at this one, as we move across the periodic table, we have more and more valence electrons. So in our sea of electron picture, I might have something like sodium, which would be +1 cations, and each of those would be providing 1 electron. If I move across here, I should have more and more electrons and a higher and higher charge for the cations. So as I move across, I see more and more valence electrons. I think the melting point should go up. It should become a stronger and stronger bonded material. And if you look at the data, that is initially happening. As you go across 1A, 2A, 3A, we see that the melting point is going up quite a bit from around, let's say, 300 to 3,000. But then if we continue on, as we add even more and more valence electrons, it comes diving down again. This sea of electron picture, it explains some things, but it really fails in this respect. Let's see how molecular orbital theory can begin to give it some insight. So if you recall with molecular orbital theory, we began by looking at diatomic molecules. We took the atomic orbitals, brought them together, and formed molecular orbitals. We could have arrangements that were bonding or nodes present that were anti-bonding. This was bringing together 2 atomic orbitals. So if I were to think about this for lithium to form Li2, we could bring them together and form bonding and anti-bonding. Now, what if I bring them together, but instead of just bringing 2, let's say I bring together 4 in a line. That's what I'm trying to represent here. I can have a bonding arrangement where all of the phases match. I could have an anti-bonding arrangement where all the phases alternate. So these might be all plus, 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 constructive interference, plus, minus, plus, minus. I now have nodes in between. I also have ones that would be sort of a partial contribution. If I think about the phases, plus, plus, minus, minus, I'd have a node in between. So I'm seeing a progression of things that would be bonding to anti-bonding. And I guess I would say completely bonding, mostly bonding, anti-bonding, completely anti-bonding. This was with 4 lithium atoms. I could look at 8. I could look at 16. I could look at 20. I could look at 20,000. What would happen if we continue on with that? I would have molecular orbitals that were bonding lower in energy than ones that were anti-bonding. In fact, if I have an infinite number, I could view this as a whole continuum of things that are a lot of different ones that are bonding and a lot of different ones that are anti-bonding. What does it mean now to then populate these? So if I look within my description right here, initially I'm adding electrons to those molecular orbitals. They're initially going into the bonding ones. As I continue on, I've reached a maximum where I've populated the bonding, and then after that, I start to add electrons in the anti-bonding. That's what it means to now weaken it. Very similar to what we saw before when we were looking at the bond order and just the diatomic. But now we're thinking about it, what does it mean where we have many, many molecular orbitals that are found within our solid? So molecular orbital theory, does it explain the trend in the melting point? Absolutely. Now, if that's all it did, meaning if that's the only thing that the theory was an advancement on, fine, but it needs to do more than that too. So what we're going to pick up next time is how do we now use molecular orbital theory and think about other properties, especially electrical conductivity, when we start to consider the structure of solids. Where does molecular orbital theory improve on our sea of electron picture? And how can we begin to use that to describe different types of materials, including conductors, insulators, and semiconductors?